Hi all, the focus of this lecture is refactoring. Refactoring is the idea of changing our source code, improving our source code, without really changing what it does. So in other words, we do this in order to improve comprehensibility, so making sure that the software or the source code is easier to be read, easier to be evolved, easier to be maintained, etc., etc., etc. And I want to connect this lecture with the previous lecture on software architecture and design. And in here, what we're going to focus on is on refactoring that tries to improve the internal design of our software. And we are going to do this in a very practical way. So I showed you a small implementation of a Pac-Man game, which is available on my GitHub. You can visit there. And we started by discussing this spaghetti version. I'm going to show it to you on my pie chart. So this spaghetti version of a Pac-Man, it is just an implementation of the Pac-Man in a single file. So for you to really understand the source code, you have to spend some time and read it. And let's see, I have 225 lines in here. Let's run so that we can get an idea of what it does. So it basically prints a Pac-Man game. So Pac-Man is here, these are the ghosts. I can move, so for example, A moves to left. I can keep moving. And the ghosts are not very smart, as you can see. Yeah, you see, I'm trying to die and the ghost is running away from me. So not very smart software, but it gives you an idea of an implementation in a spaghetti way, right? So everything is kind of mixed, hard to separate, and this is why we call it spaghetti. So in the lecture, I gave you a few minutes to see the source code. If you're following this lecture only online, do the same. And as soon as you start to do this, please try to focus on what can I improve in here. Come up with a list of problems and how you would fix them. And I also did this so in my implementation. You see lots of duplicated code, long functions, no modularity, global variables, lack of clarity, not really testable. So let's go in more details there. So first, we can see lots of duplicated code. For example, these two blocks of code in line 64 and line 199, what it basically does, it prints the map. So it goes through the map and it prints each element of the map. If it's a ghost, it prints in a way. If it's a wall, it prints on the other way. And it doesn't really matter how it does it, but we have lots of duplicated code in there. And the problem with duplicated code is that as soon as you have a change, you have to change in all the points where this code is duplicated, right? If you forget to change in one point, there will be one hidden bug that can be really tricky to find. So duplicated code is something we try to avoid. We have long functions, so if you pay attention, everything is implemented in a single file over there. It's in a spaghetti way. It has 225 lines. If you try to understand it, you saw that it was pretty hard, right? You need to have lots of concepts in your mind to understand how things really work in there. So not easy, and again, this is just 200 lines of code, right? We have seen files with thousands and thousands of lines long, which is not very nice, right? We like functions and small functions, right? Because functions, they give us more context, right? This small function does A or does B, easy to understand. And not a lot of reuse. We discussed the idea of reuse in the software architecture and design lecture, but if you want to reuse any part of my implementation, for example, let's suppose you're building a Pac-Man game and you want to reuse my UI because you liked the way I did it, you really can't. I mean, you would have to open my file and start to, extract parts that are interesting to you, but it's going to be really hard. There's no simple print map function that you could just easily reuse. No modularity. So in one single file, that file has many different responsibilities. For example, that file knows how to handle maps, how to handle the characters of the game, how to handle the game itself. There's no separation of concerns, so the user interface is a bit mixed with the game itself. There's no separation at all. We also don't like it. Global variables, I don't have functions in there, so all variables that I declare are somewhat global, so they can be accessed from everywhere. And this is, yeah, we don't like it so much. This is not a very good idea, because if the variable is global, it means that any part of my program can change it. There's no control over who changes that variable. And maybe a small part of your program changes that variable in a bad way, and then the rest of your program suffers because of it. So global variables are, and we know this because of empirical studies, global variables are a perfect place for bugs. So if you connect this with the software design lecture, what I'm basically trying to say here is that there's no encapsulation, there's no information hiding in here. So this is not a good idea. Lack of clarity, sometimes we have small pieces of algorithm in there. For example, the two blocks that I show right now to you, what do they do? Can you understand it? I mean, it's pretty hard if you look at it. Yeah, I don't know. I don't know what those things do, And I wrote this code, so clarity is also something fundamental, right? And we can add clarity by, for example, extracting these small pieces of code to functions with beautiful names. We can add documentation, code comments to explain what those things do. And it is pretty hard to test. So as you can see in my spaghetti folder, there are no tests for it. And not because I don't know how to write tests, but it's just because the way I programmed my software, it is just pretty hard to test. I cannot see really concise units to be tested, right? I do not see a way to control and observe. So I need to control how the Pac-Man walks so that I can simulate a game, but that's pretty hard to do. The game, if you also dived into the implementation, it makes use of random numbers, right? Because the ghosts walk in random ways. So how do I test something that is random, Because if I run my test, the ghost will go to the left. If I run the test again, the ghost will go to the right, for example. So how do I do it? How do I deal with this? And if we like agile ideas, so in the Agile Manifesto, one of the topics in there is that continuous attention to technical excellence and good design enhances agility. So in other words, our code needs to be crystal clear. It needs to be beautiful so that we can easily evolve the source code. And this is what we call refactoring, right? I mean, it's pretty hard to avoid having some ugly source code, some ugly implementation, but what we can do as developers is to always improve it, to always refactor it. And the book that I mentioned in here, we're not going to use this book in our course. This would maybe require an entire course on the topic, maybe a good idea for next year. The book has so many good ideas on how to do refactoring. So if you like the idea of beautiful code, please open this book. And there are many, catalogs, and this is what this book from Martin Fowler actually does. So it proposes lots of patterns on how you can, step by step, improve your code. But what we're going to do is in a different way. So I'm going to show you a version where I try to make things a bit more beautiful, more modular, so to say. And that you can find in the refactored version of my GitHub project. And by just looking at the files, you can see that I have many different files, right? So Pac-Man, program, random generator, UI. So by that, you can already guess that I have some separation, right? I have the main part of my program, the main part of my game in one file. I have the UI, meaning what takes care of the user interface in a separate file, the Pac-Man game and the business rules of a Pac-Man game in a different file. So I added some separation in there, right? I also started to break things up into small functions. So you can see this with thing borders. This basically checks if a given X and Y position is inside of a given map, right? Because I mean, if the Pac-Man is at the border and if the user tries to move it out of the border, well, I need to say, no, that's not allowed, right? You cannot do this. If given a map, where is Pac-Man? I need to find it. So I try to break up as much as possible all the business rules of doing a Pac-Man game so that it's just easier for people to understand. For example, move ghosts. So this is another function for you to explore where I basically move all the ghosts in the map in a random way. And as you can see, I'm basically, possible directions that a ghost can go. I then randomly select it and I repeat this. So hopefully this is a bit better structured, and you can now understand the source code a bit better. Also, please dive into it. But let's discuss some of the improvements. So I think the first of all, and maybe that's a very good lesson to all of you, is to separate UI logic, so user interface logic, from the rest. So it doesn't matter what type of software you are doing or what type of technologies you are using. You probably have some sort of business logic, so your software, and then how you're going to show this to the user, right? So the user interface. Um, I see groups using Pygame. I see groups using just the terminal as an output. I see groups using web development for this. So or mobile. I didn't see groups doing mobile, but mobile is also very popular nowadays, right? So there's business logic and there is UI, and you need to make sure as soon as possible to separate those two things. If you actually dive into my source code, if you check my UI file, I see that, well, I separate each one of the characters and the way I print them. And then I have, UI print, and it receives a map. So whenever I want to print the game itself, I just have to call this function UI print. I pass a map, and this function knows how to completely print a map on the screen. It also prints the final message, and it's pretty simple. You win or you lost, and I pass a parameter here. So this is basically what we do. We isolate the UI module completely. We pass all the information this module needs in order to do user interface stuff. If you receive input from the user the way I also do, because the user moves, right? There's a method, also UI key, that returns the key for me, so that, from the program, I can only call the UI module, and the UI module handles those things. It can be pretty hard to separate those two things, I know, but with more time and more experience, you're going to get very good at it. So this is something I want you to have in your mind. So separate UI from logic is a very good step towards clean code, towards maintainability. Having small functions is also something very important. Small functions not only in terms of size, but also in terms of functionality, right? It does little. One function does just one thing. Examples that I have, for example, see the function find Pac-Man, as I showed you. Given a map, it just finds Pac-Man. I need this in parts of my game, right? So as soon as the person chooses to move Pac-Man to the right, for example, the first thing I need to do is, where is Pac-Man in my map? And then as soon as I find it, I can move my Pac-Man. And I decided to isolate this behavior of finding Pac-Man in one single function. And the beauty of it is that then, functions are small. As soon as you understand this small piece of code, you understand what this function does precisely, right? You know the implementation, but also testing gets easy. So if you see my slides, I also wrote tests for it, because now it's simple, right? I just pass a map, and I just make sure that this function returns me the position where Pac-Man is. So if you're thinking about testability, having small functions also help you. So, with all the techniques we discussed, I guess you can easily do some control flow graph over there, and you can, do proper structural testing and come up with 100% branch coverage, for example. Yeah. Common logic. So it is very common that pieces of code, they look the same, but they have small differences, right? An example in there is about this is wall, is ghost, is pill. So given a position in the map, I need to know what is in there. It can be a wall, it can be a ghost, and the functions, they almost look like the same. I'm always doing map xy equals to something. So maybe I can extract it away. So I create the function is character that basically does map xy equals to the character I'm looking for. And then to each one of the functions, for example, is ghost, is pill, is Pac-Man, I just invoke the same function, and I basically change the character I'm looking for, right? So I created this generic function that checks if in that position there's the character I'm looking for in there. Maybe this example is too small, because even the previous code was not that complicated. But try to generalize this to something more complicated. So maybe the common behavior is like 10 lines long, right? And then if you have 4 methods, you're going to have 4 methods with 10 lines long, where 90% is the same. And then odds, chances for bugs, they just increase. So as soon as you start to observe common logic, extract it to a single method and try to reuse this method in other places of your program. Let me see, what I want to say in here is it is about breaking large behavior into small behavior. So if you pay attention, this part can be moved to a separate method, which I basically showed in here. So back then, we basically need to find all the ghosts, right? So this is something that I do to find all the ghosts in the map. And then for that on, I continue for each ghost in all the ghosts. So I need to find all the ghosts first. So why not extract it? So if I create a function get all ghosts that does this magic, then the move ghost function gets way simpler. So for ghosting, get all ghosts. Yeah. So we discussed a lot about abstractions, and if you think about it, a function is also it allows us to create abstractions as well. So they just created this ideal of getting all the ghosts. And if you kind of don't look at the get all ghosts, but you only look at the move ghost function for ghosting get all ghosts, when you're reading this piece of code, you kind of don't care about how we do to get all the ghosts. You just know that this function will return all the ghosts to us. And in a way, that is the beauty of an abstraction, right? It let us talk about things without really caring about the implementation. We focus on higher level problems, things, concepts. And you know, the higher level it is, the easier it is for people to understand it. If you see this previous version, if you dive into it, you're gonna have to first understand that this is getting all the ghosts so that I can loop on all the ghosts. In here, you kind of don't have to pay the price of understanding how we get all the ghosts. We just move from there. So extracting, breaking up large methods to small methods not only helps us to have smaller methods which are easier to understand and easier to test, but they also allow us to create abstractions that would then facilitate the overall comprehensibility of our implementation. There are no global variables in my implementation anymore, so all the global variables in the previous version like map, win, and game finished are local variables. So in a way, they belong to a smaller scope, so they are only visible inside of a function. And basically this means that the smaller the scope, the bigger the control, right? So the less parts of my software that can touch one variable or change one variable, the less number of bugs I'm gonna have, right? So adding restrictions is always good, right? Reducing the spots where a problem can happen is always very good. And also the map. In the previous version, the map was a global variable, and this means that changing the map was something tricky, right? It's tricky in the sense that, I mean, I would have, if I wanted to have a new map, I would have to load it into a global variable. There's less control. You know, anyone can put a map in there, and the map is basically a matrix right now. Anyone could just go there and do map equals 10, you know, and this is just wrong. You cannot have a map that is equals 10. So, you know, like putting an int inside of a matrix, we have less control. And now map is a parameter, so I have to pass it through all the methods. And this is better because it gives me control. So outside of these functions, this map is created and I only pass the map to the functions. So functions kind of don't care about how this map was created. But it also facilitates testing, right? If I have a small function and it receives a map, I can pass any map I want to this function, and this function can be tested, right? And we're going to get to testability soon, and you're going to see what I'm talking about. And testability. So if you see this version, I have lots of test code for it, and it was just because it was easier, right? There are so many things I can talk about testability in here. Let's just go one by one, and then I'll go to the source code soon. So first, lots and lots of tests. I was able to write it. For example, the within borders, the function we discussed before, given a map, it tells us if x and y are within the map. It is because this behavior is isolated. Now I can write lots of tests, right? And it took me, a few minutes to write a lot of them, and I applied boundary testing in there. And guess what? I found a bug. So true story here. So when I implemented the spaghetti version, I didn't test it. When I extracted things to smaller functions and I was able to test, I was able to find a bug, right? So I think I had a smaller than or equals where it should be just smaller than. So you can actually find bugs because now it's easy to test. I was able to write system tests. So system tests are those tests that execute our entire software because I was able to have more control and more observability. So let's just dive into these tests so that you can see it. I call it program integration tests. And basically you see I have a map, and because I can control the map, I can come up with very small maps, right? I could fake the key setup. So in here I'm saying that, well, left is happening because A is left and left is happening again. And I can run my software and I basically pass all the inputs. So I pass the map, I pass the function that prints on the screen, I pass the fake UI key because now we're not getting the key from the keyboard, blah, blah, blah. And if I run it, this is what happens. So I see 3 maps, right? So one is here, then the person moves, then we go to this one, and then we go to this one. And for some reason I have to win in this test case. The same for the lose. So if I run, so in this one I guess I'm going towards the ghost. So I go closer to the ghost, closer to the ghost, closer to the ghost, closer to the ghost, and then I die. Yeah. So because my source code is better structured now, I can easily control, which means I can send the key presses I want my software to simulate. I can pass a simpler map, and I can observe. So you see that the function run returns the 2 variables for me if the game is finished and if I win or not. And I can easily do assertions on this, right? Look at this. This is very easy to do, right? So the game is finished and win is false. I lost the game. So controllability and observability, right? We discussed this in testing lectures, but I guess now you can really see what I'm talking about. What else? And about the randomization, right? So playing with random numbers is tricky. So what I do is I also simulate the random generator. So instead of generating random numbers for my test, I generate numbers that I know, that I'm conscious about, so that I know what my system will do. So I know that my ghost will always go to the right, because that's how I'm simulating it, for example. So again, controllability. Yep. Flaky tests, I discussed this about before. So if I have random behavior, so ghosts walk through different directions every time, how can I make sure that my test is not flaky? And a flaky test is a test that sometimes passes, sometimes it doesn't pass, right? So if I'm looking for the test where I win the game, maybe you know the ghost does a random walk in there and the ghost finds me before I can win the game. Because I can control things now, this doesn't happen anymore. I know that my ghost will always go to the right, my Pac-Man will always go to the left, it's gonna eat the pill first and then eat the ghost, so I can control. So in this way I avoid flakiness. Let me see what else I have in these slides. So in here I wrote everything that I'm talking about in terms of texts, but the best for this lecture is to dive into the implementation, okay? And try to see why this implementation is a bit better. And finally, I want to close this lecture by basically telling you that there's a big relationship between how good your design is and how easy it is to test. So good design, good software design means it's just easier to test. And the way to get to good design is by means of refactoring. You have to refactor and refactor and refactor. And I mean, in practice, I cannot really see you coming up with the best design from the very beginning, right? Because the more you program, the more you learn about the business, the more you learn about the abstractions you need to have there, the more you learn about the technical challenges of implementing all those things. So you keep improving, right? Until you get to the best design ever. If ever exists, right? So that maybe there's something, there's always a way to improve, but at some point you just reached a very good point. Just to finalize this lecture, I'm not going to discuss this. So we have the spaghetti source code, source folder in here with the spaghetti code, the refactored code that contains basically separation into files, where I try to basically separate the main concerns I see, UI, the business rule, the game engine. And I have the OOP version, so the version that tries to use object-oriented programming. And this is a good version, a good piece of code to explore as soon as you learn a bit more about OOP. Yeah? So this is the goal of this refactoring and design lecture. I want you to have in mind that you always have to improve your software, and improving means making sure your design gets better and better and better. In here, of course, I didn't discuss what we call low-level refactoring, which is, I have this variable, and the name of this variable is not very good, so I can change the name of the variable. Those refactorings are also fundamental, and you gotta do them, but they are more natural to understand from the very beginning of your programming life. Refactoring design is trickier, and this was the whole goal of this conversation. Yes? See you next time.